Hello, Step 300 students. Okay, today we are doing section 3.3, more confidence intervals, except this time we're doing them for means. So remember that a confidence interval is just a way of estimating our population parameter, whether that population parameter is a proportion or a mean that we are interested in. So previously we've looked at proportions. So today we're going to take a look at means. Not a whole lot of difference the way that we construct the confidence interval. We take our statistic, our sample statistic, and we add and subtract the margin of error to create an interval of values. Okay, this was just directly to the shortcut where we're building that interval by taking a multiplier. 2 is the usual one to approximate a 95% confidence interval. So we take the multiplier times the standard deviation of the sampling distribution. That created our margin of error that we added and subtracted to our statistics. So the multiplier is 2 when we're approximating a 95% confidence interval. So 2 standard deviations above and below. We add and subtract it to our sample statistic. When we wanted a different confidence level, that multiplier changed. For proportions, we called it the Z multiplier. And it depended on the confidence level. So 90%, we would use a smaller multiplier. For say 99%, remember, was a larger multiplier. We basically just went out farther. And that's what we did for proportions. We used a Z value, critical value, according to the confidence level. 2 is used for an approximate 95% confidence interval. So that was from the previous section 3.2. We learned about different multipliers for different confidence levels. And recall that the 1, if we wanted something a little bit more precise for 95%, we didn't use 2. It was actually 1.96. Okay, that was for proportions. So again, today we're looking at means. So now for means, we have to use a T multiplier instead of the Z multiplier. So the multiplier is now simply called a T. Okay, we're going to come back to more details on that in a few minutes. But for right now, it's still created the same way. We still take our sample statistic, except now it's going to be a sample mean. We're going to add and subtract this margin of error. We can still use 2 for the multiplier if we're doing a 95% confidence level. We can still approximate it using a multiplier of 2. And our standard deviation of the sampling distribution, now that we're looking at sample means, if we go back to the central limit theorem on sample means, recall that in order for a sampling distribution to be approximately normal, we needed our sample size to be greater than or equal to 20 for sample means. Then we knew we had a approximately normal distribution, bell-shaped, centered at the population mean, mu. So that means the mean of all of these sample means is going to be mu. The standard deviation of the sampling distribution is the standard deviation of the population, sigma, divided by the square root of the sample size. Remember, the sampling distribution of sample means is far less variable than the standard deviation of the population or the standard deviation of the sample. So if we are using the standard deviation of the population, we would take that over the square root of n. That would be the standard deviation of our sampling distribution. Most often though, we do not know that value, so we're going to substitute it with the standard deviation from the sample, and that's simply called the standard error. It's an approximate value for the standard deviation of the sampling distribution. So remember, we worked with these previously and they turned out to be very similar values. Okay, so the standard error is simply substituting S for sigma because, again, usually we do not know sigma. So this will be the standard deviation of the sampling distribution. So when we are up here and we create our confidence interval, this is how we will calculate our standard deviation of the sampling distribution. Okay, in the book, you read about an example of prices of used Hondas on the internet. Okay, they found a sample of 102 prices of used Hondas on the internet for a certain month, and that average, the sample average, came out to $13,292. That sample of 102 prices had a standard deviation of 4,595. So this was our sample. These are our statistics, our sample mean and our sample standard deviation. So if we wanted to approximate the 95% confidence interval, we can use a multiplier of 2. We would take our sample mean and add and subtract 2 standard deviations of the sampling distribution. This is actually the standard error because I'm using the standard deviation from the sample because I know nothing about the standard deviation of the population. So this, in the parentheses, 4,595 divided by the square root of 102, that value is the standard error of the sampling distribution of all sample means of this size. Okay? I'm going to take 2 of them, 2 times that. That is my margin of error. That is the amount that I'm going to add and subtract from my sample mean. So here I subtract it. That's my lower end of my interval. Here I add it, and that's my upper end of my interval. So now what I've done is I have created my 95% confidence interval, my approximate 95% confidence interval. Because similar to the proportions, 2 is just an approximate for 95%. If we want to get more precise, that is when we're going to need to look up t-values, and we'll do that next. So for now, we would interpret this confidence interval like so. We are 95% confident that the average price of a used Honda found on the internet at this time is between $12,393.94 and $14,190.06. Now we're talking about means, not proportions, so you need to put the units on whatever it is your values are representing. Here they're representing actual dollar values, so I'm using dollars. So when we're talking about sample means, it's going to change. Whatever it is we're talking about will change from study to study to study. So we need to include the units. Okay, now let's talk more about this T multiplier. We mentioned before about a T distribution. The T distribution, it's called the student T distribution because the person that basically created it and studied it and used it and shared it with the statistical world worked for Guinness Brewery, and they did not want him to publish under his name because they did not want to be associated with it. But it turned out to be a good thing. So he published it under the name Student. That was his pseudonym, Student. So that's why it's known to this day as the student T distribution. Remember, it's a family of curves. We briefly talked about this in class. It is a family of curves, a bunch of different curves, because it depends on the sample size. Remember, the smaller our sample, then we have more variability. The larger the sample, we have less variability. No matter what, they're still normal, bell-shaped, and they're symmetric. Okay, so I'm going to kind of demonstrate this on a little app called GeoGebra. So give me a second here to pull this up. All right. Here is the little app. It's called GeoGebra, all right? And with this app, I'm gonna kind of give you a little picture of a family of curves. So up here, let me just explain a few things first. Degrees of freedom. If you recall, degrees of freedom were one less than the sample size. So if my sample size was 5, my degrees of freedom would be 4. If my sample size is 10, my degrees of freedom would be 9. If my sample size is 102, like the used Hondas, my sample size or my degrees of freedom would be 101. So the dotted line right here, the dotted curve, is the normal distribution. The orange or red one, whatever color, you can see that in there, is the student T distribution. So this is for a very small sample size 5. Notice how it is squashed down. It's a little bit lower, and then it's wider in the tails because it's more variable. It's more spread out. So right now I have it on a critical value of 2. So there's my critical value of 2. That would be the multiplier, okay? The T or the Z multiplier, all right? But notice that for the normal curve, let me show you, click on this box. Here is 95%. Well, it's almost 95, 95.45, because remember 2 is just an approximate value. 1.96 would be exactly 95, but I had a hard time moving this to be exactly 1.96. So if you see, I can move this. There's 1.83. I couldn't get it to go to exactly 1.96. But notice that that is 95% of the value. So remember that the remaining 5% is split between the two tails above that and below that. So remember that this goes with the little dotted curve. So you can see in that dotted curve, underneath that dotted curve, in that space right there, is 0.025, that area, 0.025 on both of those underneath the dotted curve. You can see underneath the red curve, it's a lot bigger. So you can see underneath the red curve, that area is a lot greater. As a matter of fact, if you look over here, when our critical value is 2, I have 88.39%. So the shaded region right here, which for the normal curve was 95%, now for degrees of freedom of 4, it's only 88.39%. So the other 12% approximately, right, that makes up 100%, 88% and 12% make up 100%. So that 12% is split in half into the two tails. So right here is 6%, whereas with the normal curve, it was 2.5%. So you can see that there's a lot more data in the tails. So if I wanted a 95% confidence interval for a sample of size 5, sample means, I have to go out farther. So watch what happens when I move my t-score. I'm going to be looking for 95% over here. So I'm going to move this. So now it's around 90, 91, 92, 3, 4. There, 95.05. So see how far out I had to go to capture 95%? I'm at a critical value of 2.79. The normal distribution is 99 at 2.79, 99.5 approximately. So with degrees of freedom, watch what happens. I'm going to put this back to 2 for a second here. Okay, now watch what happens when I change my degrees of freedom. So this curve right here represents 4 degrees of freedom, or sample size 5. So notice that if I get a larger sample, notice what's happening to my curve. It's moving up toward the Z normal curve. And notice down here, this also is getting closer and closer to the normal curve. So this is a sample size of 19. So here's 19 degrees of freedom. So this would be a sample size 20. And this little applet allows me to go all the way up to 30. Notice that at 30, we are pretty much the same as the normal curve. Again, if my sample size gets smaller, my curve is starting to widen out a little bit. So I have to go farther out to capture 95%. So the T multiplier is going to not only depend on the sample size because the curve is changing, but it's also, just like before, going to depend on the confidence level. So we were just simply looking at 95% and talking about that. But if I wanted 90%, I'm still going to have to, or excuse me, 99%, I'm still going to have to go out farther, just like it was true for the Z. And then for a 90% confidence interval, I'll have to go smaller. Okay, if I don't want 95%, 90%, I would go smaller. I would come in here. Ooh, come in here more. Okay. Let me go back to my notes. So the T multiplier is what we also know call the critical value, is determined by the sample size and the confidence level. So if we'll be able to do this on our applets, but because the curve changes according to the sample size, we have a table that we need to use to find the T multiplier. Let's just look at 95%. This table that I have right here goes all the way. Here is the degrees of freedom in the first column, and then various confidence levels, all right? So the degrees of freedom, again, 1 less than the sample size, goes all the way up. Once we get to 30, notice it starts to jump. 40, 50, 60, 70, 80, 90 to 100. Notice when we get beyond 100, they're pretty much the same values. These are exactly the same values as the Z scores. There's my 1.96 for 95% confidence. Let me see if I can get that whole thing. So using, say, the Honda example, I could just use the Z score, 1.96, because my sample is larger than 100. For a 99% confidence interval, I would just use 2.576. For 90% confidence interval, I would use the 1.645. These values are basically the same as the Z multiplier because our sample size is so large. So again, if I had a sample of size 10, I would have 9 degrees of freedom. If my sample size was 10, this would be the multiplier I would use for 95%, 2.262. If I had a sample of size 5, then I would use the 4 degrees of freedom, and my multiplier for a 95% confidence interval would be 2.776. So you can see how much bigger this is getting the smaller my sample, because I have to go out farther to capture the same amount of data because of the fact that my curve is getting lower and getting more spread out. I will come back to that when we do our activity. Okay, that's it. I'm going to close this one. This is basic notes for this section, okay? And I'm going to have another activity, 3.3 activity that we'll walk through on the second part for today.